Hi everyone, welcome back to Physics 142. It's another sunny day here in Valparaiso, Indiana when I'm recording this, and so I hope that there are many moments of sunshine, both literally and figuratively, in your life right now. In this video, we're going to learn something new. We're going to learn about something called Ampere's Law. But to do that, I first need to review a couple of concepts so that we can understand the context for Ampere's law. And one of the concepts that I want to review is I want to review the idea of line integrals or path integrals. So we have seen these sorts of integrals before. Basically, a line integral is something we're integrating over some path, maybe through a vector field, and we've seen several of these before. So I'll just give you a couple of examples. One is our formula for work. You might remember that work is force over a distance, right? And if we have changing force, or if we have some sort of curvy path, then we say work is the integral over some path, whatever path we choose to walk, of force dotted with each step that we take along that path, right? Force dotted with distance, our little path dl, right? Each little step that we take, and we think about the force for each step, when we add all of that up, we get the work, right? Similarly, we had another one recently where we looked at electric potential. And when we are computing electric potential from electric fields, again, we integrated over a path. We walked in some path through an electric field, and we took the dot product of the electric field with our steps dl, and when we took that integral, we ended up getting the amount of potential, the potential difference, how much our potential changed, and it depended on what path we walked here. So it was all about taking a bunch of little steps through a vector field. For Ampere's law, we're going to be interested in walking paths through magnetic fields. So just to sort of think about that, all right, let's imagine that I have some sort of magnetic field. So I'll draw it here in red. So let's just imagine we have a magnetic field. All right, so this is a magnetic field B. I'll get my hand out of there in a second. And let's just give B some magnitude. Let's say it's 1 Tesla. All right, so here's a uniform 1 Tesla magnetic field. All right, and now, maybe it would be useful if I chose some coordinate system, right? So let's just choose an X, Y coordinate system here. And you might imagine that, I could walk in some path through this magnetic field, just like we walked a path through the electric fields with potential, right? So let's think about walking some path through a magnetic field. So we'll do that. So walk sort of along it, and then maybe I turn and I'll walk perpendicular to it a little bit. All right, and let's say I walked maybe 10 meters this way and 10 meters this way. All right, so first I'll walk 10 meters this way. All right, and then I'll walk 10 more meters in positive y there. And so if I wanted to take sort of a path integral here to represent what was going on, all right, what I would do is I would say, well, let's take the integral over my path of B dotted with dl. All right, let's just let's think about sort of similar to taking E dot dl. All right, what if I do B dot dl? What's going to happen here? All right. Well, with these path integrals, where we're integrating over one of these dot products, what we want to do is we want to split the integral up into different pieces, right? The pieces where our direction changed, right? As long as we're going in one direction, well, this dot product will always be the same, right? If we change directions, that will change this dot product, and so then we need a separate part. So to sort of integrate over this path, I might think of this as the first part. This is the second part, and so I'm going to do the integral over sort of part 1, right? Part 1 of B dot dl, right? And then I will also do the integral over part 2 B dot dl, right? So there's another this would be how I accomplish this integral. I split it into two different pieces. Well, now that I've split it into the two different pieces where I can evaluate the dot product, I see that, well, the first part, I'm going to be starting at some position 0, going to some position 10 meters away, right? And I'm going to dot product is B times dl, the magnitude of B, that's a Tesla, times the magnitude of dl, which are all of my little steps, times the cosine of the angle between them. In this case, they're going the same way. For the first part, that's going to be cosine of 0, which we'll remember cosine of 0 is just 1, all right? And then for the second part, we will go ahead and turn and walk uphill now, or if you're sort of in the positive y, perpendicular to the field. And so there I'll start at y equals 0 and go to y equals 10. Again, b dl, and then now I have a cosine of 90, right? Because they're going to be perpendicular to each other. And well, cosine of 90, that's just 0, so that means this whole term is just 0. So now I can go ahead and just evaluate the rest of this here. All right, B is a constant 1 Tesla throughout this integral, right? So I can pull it out. So we'll just say we've got 1 Tesla here. And we're going to integrate from 0 meters, x equals 0 meters, to x equals 10 meters, dl times 1. And so that's just going to be 1 Tesla times 10 meters minus 0 meters. All right, and so that is just going to be 10 Tesla meters. All right, 10 Tesla meters is this integral b dot dl, and that doesn't have a special name. It's not we might think sort of similar to potential, all right? But this is sort of an amount of stuff, right? Just like potential is some amount of stuff when we add up all of that magnetic field, right? That's sort of, we're adding up something, right? Something. And that something that we add up is going to be pretty relevant in just a couple of minutes. But importantly, it's important to know that while we started with vectors, right, we started with things that have direction, right, these b and dl's, when we take that dot product, we get rid of the direction, right? So we've just, in the end, just added up an amount of stuff here. So this is a little piece of review that is going to be helpful then for understanding Ampere's law, and we will go into that in full detail in the next video.